Hello everyone. I know the class is a little bit of a mess right now as we're trying to get through the last homework submissions, but I wanted to take some time to show you how to make normal mapping work. So you might recall at the end of one of the classes we were taking a look at normal mapping and I was coding and having everybody follow along, and we were running into some issues. It turns out that the code was all okay. So if you have code from inside of that class, then you should be fine. The real issue is that I should have taken the time to properly create the assets in order to give us an object space normal map. Using ones off the internet really just isn't going to work. Luckily, creating normal maps in Maya is equally easy to creating ambient occlusion maps. So it'll take only 10 minutes at most. You should do that before watching the rest of the video, and we're going to go into the code. I recommend the first video that comes up when you search Maya normal map baking. And I'll show you how to put together a normal map really quick through the use these two boxes here. One high res and one low res one. So you really don't need a lot of modeling experience, but you should make a couple of models from scratch and have something unique to show me for homework tomorrow. So I already put a couple things together. I have a sphere and I have its normal map here. Of course, I'm not an artist again, but it doesn't really matter, right? So you might notice we're working with a really old version of the framework, and the reason is we really don't need any of the fancy stuff. In fact, I've put my repo back to a point where we didn't even have frame buffers yet. But that's okay. In fact, the code is going to be extremely quick. So the first thing we want to do is go into our game.h, and in fact we can just change the grass texture object, rename it to normal texture to load in our texture. Now of course you could load in the normal map and an actual color texture, but in this case we're really only concerned about how the shading algorithm is going to change, so we can discard the color texture for now. Instead of our monkey, I'm going to use my new model, which is a sphere, so I'll name it accordingly. Now the sphere I'm going to leave at the origin, but I'm going to have my light rotating around the scene, so I'm going to rename this transform I have at the end to light transform. That's all we're going to need for the header file. If we go into game.cpp, we can change around the errors. So up here in the destructor, we're going to change the sphere. We're going to have our sphere load from file instead, and that's going to be sphere.obj. Speaking of, I should probably move these into their respective folders. My normal texture can now read normal texture.png. Down here, my light transform should be the one rotating around X. Our model matrix being passed in as the monkey's transform, we don't have anymore, and we don't want our new sphere to be having any of these transformations. So I'm going to create basic identity mat4. In fact, I can do this even more readable, why don't I? If you're using Minimath, you can get an identity matrix. Where is it? Here we go. You can simply request an identity matrix, and then of course we want to get the float array, so I'm going to call data. Instead, light transform is now going to be used when calculating the light's position. So this point light is now going to conform to the rotations around the scene. I can insert that into the middle here in order to have the correct transformation of space, starting in world space here, rotating around a bit, and then with the inverse camera matrix I can convert to view space, because of course you might remember everything we're doing in the shader is going to be in view space. Our grass texture here is now going to be our normal texture. That's going to be bound and sent into the shader. Our VAO is now going to be a sphere.vao. We're going to get sphere num vertices. So that's all that we need to do for the CPP file. What I would like to do is up here, when we pass the texture in, I'm not passing a color texture anymore. Let's rename this to normal map to be a little bit more readable. The only thing we need to finish this up is to jump into the shader and utilize the normal map to read our normals rather than getting them from the source mesh. So I'm going to pull up our shaders here. I'm back into a version where the only ones we had were the pass-throughs. However, if you're using a newer version, pass-through.vert would be more or less equivalent to our static geometry, and our pass-through.frag would be our point light, which we later converted to a directional light. So I'm going to drag both of these into Visual Studio to work with them. Pass-through.vert, we can remove a couple things. We can begin to ignore the normals coming in from the mesh. We don't need those anymore. Because we removed those, we're not going to be passing them forward into the fragment shader. We can remove that out. And of course, in the body of the shader itself, we can remove the calculation of the normal. If we go to the fragment shader, we can rename our sampler to normal map, and we can remove the invec3 norm because of course we're not expecting one from the vertex shader any longer. Looking just a little bit further down, we have our normal, which used to be from the vertex shader, being normalized here to account for the rasterizer interpolating it across the face. This is going to change though. This is going to look different now. Our normal is now going to be a texture read. We're going to be taking our normal at a very high density of detail from the texture. Detail that interpolating across a face cannot provide. So we're going to get very, very fine control over the normals across the triangles as opposed to just specifying them per vertex. So we can read from our normal map at the corresponding texture coordinate. I'm going to cast using a swizzle to XYZ. Then I'm going to unpack. So I'm going to multiply by 2.0 and subtract 1.0. And I can delete the old line. If you don't recall what the unpacking is about, we went through it in class, but I'll cover it again really quick. Textures saved to file are only allowed to have the range between 0 and 1. However, if you imagine a normal, if you hold out your finger and you anchor it at the base and you try to spin it all around, you can find orientations where one of the axes must be negative. So in order to have normals that can point in all quadrants of a sphere, we actually need the range of -1 to 1. So because of the fact that textures can only store 0 to 1, what happens is 3D modeling software compresses the normal from the larger range to 0 to 1 before writing it to file. This means that when we read from the texture, we need to unpack it in order to restore the original values that should be read. So we can do that with a simple linear transformation. If we were to take something that's between 0 to 1, and we multiply whatever value that is by 2, we now have any conceivable value between 0 and 2. If we then take that resultant value and subtract 1 from it, we then bring the entire range uniformly down to -1 and +1. So with that in place, we have the original normal as it should be used. We don't have to normalize as we did with the interpolation across the shaders, because the 3D modeling software would have written a normalized normal that even unpacking it doesn't break the integrity of the normalization, so we don't have to bother to do that again. So by using the same name, normal, it's automatically going to start being used throughout the lighting. If you recall what this is going to do, we're going to determine first the distance between the point in space and the light. Going to determine how much the surface is facing the light. If the surface has some sort of influence from the light, we're going to go ahead and compute our actual diffuse and specular light, which consists of first accumulating the attenuation value, calculating our diffuse multiplied, of course, by the attenuation and scaled also by the factor of how much we are facing the light. Then we compute our specular value using the Blin-Phong method, and we apply our specular in a similar way, scaled by the light specular exponent. After that, of course, everything comes together. We start multiplying the texture color by the lighting that was calculated here. Of course, the issue is we don't actually have a color texture anymore, so I'm going to replace this texture call with a simple vec4 containing something like 0.66 all the way across, just a flat, relatively dull color with a 1 on the end. Of course, if you wanted to have a proper texture, simply include another sampler and read from that texture here. However, if we are to run the program now, we'll have a grayish sphere with a light that is circling around it. It's going to come around again. And although, if you look at the silhouette, you can see that it is very much just a basic Maya sphere, our normal map, which we can see here, is certainly being applied to the scene. Oh, I wonder what happened here. I must have probably interjected some vertices unintentionally. But regardless, you get the idea. So generating a normal map like this on your own object really just takes 10 minutes. I expect you to do it and to have a result that looks similar to one like this, where it's obvious at a glance that the normal mapping is working. There have been examples before that I've seen where I've had to really stare at it for a while to try to see if the light is actually interacting with the object correctly. If that is the case, probably won't get full marks, considering just how quick and easy it is to create a stable version of the program. So that's what I'm looking for when it comes to normal mapping. Really not such a daunting task. This is going to be our last video, so unfortunately I won't be making any more and I'll miss that, but I'll see you all tomorrow and on Friday in class. Bye.